Hello, future engineers. If you're still new to my channel and you like what I'm doing, please subscribe and share my videos to your friends and to your friends' friends. This is the only way you can help me promote my channel. And you know, this work is very tiring on my part, but I will be keep refreshed and inspired if you also share or do your part by helping me uh, explore my channel so that others can also explore. So it will be helpful in your studies, especially civil engineering students like you. So this is example 4 on stresses in beams. I hope that you can follow the solution and be able to develop your analysis and understanding on stresses on beams. For the timber beam section shown, the maximum bending moment is 18 kilonewton meter and the maximum vertical shear force is 4 kilonewtons. So determine letter A, the vertical shear stress and the bending stress 100 mm from the bottom of the beam. The vertical shear stress bottom of the beam section. The vertical shear stress and the bending stress at the junction between the flange and the web, and the maximum shear and bending stresses in the section. So this is the given section. So because formulas involve moment of inertia and the section is not symmetrical with respect to the horizontal axis, so in locating the neutral axis, we have to compute the areas first. So this is the level 100 mm from the bottom where we investigate the shear stress and the bending stress at this point 100 mm from the bottom surface. And since this is 200, so that's also 200. So I'll call this area 1. That's the location of the neutral axis expected. We will call that area 1, this one as area 2. So area 1 is 250 times 50 mm. So it is 12,500 mm square, while area 2 is 50 mm by 200 mm. And therefore it is 10,000 mm square. Therefore the total area is equal to 22,500. 12,500 plus 10,000, 22,500 mm square. So in locating the neutral axis, we use Varignon's theorem and we will call this C top and this distance C bottom, where C bottom is 200 plus 50 minus C top. So by Varignon's theorem, area total times C top is equal to area 1, which is 12,500. Then the distance of the centroid from the top is half of 50, so 25. 12,500 and 25 plus area 2, which is 10,000. Then this is the centroid. 100 plus 50 is 150. So 150. So from there we can solve C sub t equal to 80.56 mm. Therefore C sub b is 200 plus 50 minus C sub t. So C sub b is 250 minus 80.56. So it is 169.44 mm. So the vertical shear stress here, let's consider the area at the bottom. You can also consider area at the top, but it's a bit complicated. There are two areas involved and portion of the area is below the neutral axis, other portion above the neutral axis, so it will be a bit complicated. So instead we use the area at the bottom, then from the formula. So since C sub B is 169.44 minus 100, therefore the distance of this point from the neutral axis is 69.44, 169.44 minus 100. Then this is the centroid of this area that we will consider in computing for Q. Q is area times distance of the centroid of area to the neutral axis. So since this is 50 plus 69.44, so that would be 119.44, this distance. This is y prime supposedly. From Q equals area prime y prime, where area prime is 50 by 100 and y prime is 119.44. So this is the centroid of the area of the flange. Its distance from the neutral axis is half of 50, 25, or C sub t, 80.56 minus 25. So that would be 80.56 minus 25 is 55.56 mm. While this is the centroid of the bottom of the web area, this 50 by 200, so because this is 100, that's the centroid, and its distance to the neutral axis is 69.44. So I, moment of inertia, is by transfer formula I sub Cg plus area distance square. For the upper area, the moment of inertia is 250 base h cube over 12. So 250, 50 cube over 12. Then we transfer the moment of inertia to the neutral axis, because this is moment of inertia with respect to the neutral axis. So plus area, which is 12,500, distance square, the distance of the centroid of the area to the neutral axis is 55.56, so that's why you have 55.56 square. Then plus the moment of inertia of this web transferred to the neutral axis, so it is 50 to 100 cube over 12, then plus area 10,000, and the distance to the neutral axis is 69.44, so that's why you have 69.44 square. So remember that you are expected to know already how to compute the moment of inertia, because if not yet, then you're not supposed to be in this course. You have gone through with statics, and this was discussed in statics, also in integral calculus. So therefore I is 122.74 times 10 to the 6 mm to the 4th. Then shear stress formula, VQ over IB, where shear is 4,000 newtons, Q. So as I said, we consider this area here. It is equal to area of this portion below this section, which is 50 by 100, and its distance to the neutral axis is 119.444. So that's it. So shear stress is 4,000, Q is 50 by 100 times 119.44 divided by moment of inertia 122.74 times 10 to the 6. Then B is the width of this section, which is 50 mm, this blue section line. So solving for shear stress in megapascals, it is 0.3892 megapascals. So let's express the answer to kilopascals times 1000. So shear stress at this section is equal to 389.2 kilopascals. Then likewise, for the bending stress at this section, it is below the neutral axis. The moment is positive, so therefore it is mildly. So the top fibers above the neutral axis will be in compression, and the fibers below the neutral axis will be in tension. Therefore, this is in tension, where y is 69.44. So bending stress formula, my over I in general, where moment is 18 kilonewton meter, or 18 times 1000 square newton mm. Y is 69.44, this distance here to this section. Then moment of inertia we already computed. So bending stress at this point or section is 18 times 1000 square. Y is 69.44 divided by I, 122.74 times 10 to the 6. So cancel 1000 square and 10 to the 6. So 18 times 69.44 over 122.74, that would be in megapascals, and it is tension at this point. Then we proceed to part B, the vertical shear stress and the bending stress at the junction between the flange and the web. So here at this point, so we still use this formula, VQ over IB. So this time we have, this is the junction, we have areas above this junction, which is easier because this is 12,500, and area below this junction, which is this one. However, there are two areas to be considered if we consider the area below this junction. Area below the neutral axis and area above the neutral axis. So a little bit complicated, but I will give you I will only dictate the alternate solution considering the complicated case. So that the simpler case is if we consider the area above the junction in computing for Q. So Q is just this area here, which is 12,500 times distance to the centroid, which is 55.56. So I'll give you the alternate solution so that you will also be exposed on how to compute for shear stress whenever two areas are to be considered. So shear is 4,000. Then Q is area above the junction, which is 12,500. Then the moment arm to the neutral axis is 55.56 divided by I, 122.74 times 10 to the 6. Then the width of this junction between the flange and the web is still 50 mm, this one. So it is 50, then we multiply 1000 to convert shear stress at the junction in kilopascals. So shear stress at the junction between the flange and the web is equal to 452.7 kilopascals. So the alternate solution, what if you consider the area below? So if you consider the area below, take note that there is area below the neutral axis and there is also area above the neutral axis. So you treat the area below the neutral axis as positive. So the alternate value of Q is 50 by 169.44, this area here. So this is the alternate Q. 50 times 169.44, then its distance to the centroid is 169.44 divided by 2. So again, the alternate Q is 50 by 169.44 times 169.44 divided by 2. Then you have to subtract this area, moment of this area to the neutral axis, which is 50 times, this distance is 80.56 minus 50, so 30.56, so that's 30.56. Then times 30.56 over 2. Again, the alternate value of Q is, if you consider area below, is 50 by C sub B, 169.44. Then moment arm to the neutral axis, 169.44 over 2. Then minus 50 times 30.56 times 30.56 over 2. And you will arrive at the same answer, supposedly. So that's it. Then for the bending stress, it is above the neutral axis. This time Y is 30.56. So bending stress at the junction is moment 18 times 1000 square times 30.56, the y, divided by I 122.74 times 10 to the 6. And this time, because this is above the neutral axis and the bending moment is positive, it is compression. So in megapascals, 4.482 megapascals compression. And finally, the maximum shear and bending stresses in the section. Remember, the maximum bending stress occurs at the outer fibers, either top and bottom. We will compute that. There is maximum compressive stress and there is also maximum tensile stress. We will compute each for the bending stresses. Maximum bending stresses. For maximum shear, it occurs at the neutral axis. And again, there are two areas. One is above the neutral axis and the other is below. So the simpler area would be this area below. So we will use this for Q instead of the area above, because there are two areas involved. So for shear stress, we still use this, but the maximum shear stress occurs at the neutral axis, so that Q is this area here, which is 50 by C sub B 169.44 times distance of centroid to the neutral axis 169.44 over 2. Then B is still 50 mm. So tau max equals 4000 times Q, which is 50 by 169.44 times 169.44 over 2 times 1000 to convert to kilopascals. Then divide by 122.74 times 10 to the 6 moment of inertia times 50. So tau max is equal to 467.8 kilopascals. Then for bending stress maximum in compression, so we use this formula, but y is replaced by C sub B and C sub T. C sub T and C sub B. So sigma max in compression, which occurs at the top fibers, 18 times 1000 square, C top 80.56 divided by 122.74 times 10 to the 6. So don't mind 1000 square and 10 to the 6. Sigma max compression, maximum bending stress in compression, which occurs at the top fiber, topmost fiber, is 11.81 megapascal. So that is in compression. Then bending stress maximum in tension, which occurs at the bottom fiber, bottom fibers. So sigma max in tension 18 times 1000 square. C bottom is 169.44 divided by moment of inertia 122.74 times 10 to the 6. So sigma max in tension is equal to 24.85 megapascals. So that's it for this problem. I hope that you were able to follow and understand the solution, the explanations. This is a very nice example for this problem, but the maximum bending moment is given and the vertical shear force is also given. The more challenging problem would be if this maximum moment and shear force will be determined in the given beam and the loadings. So here they are given, so that's why it's not so challenging. That's it.